Today we're going to talk about a network compression example. So we're going to solve this problem and see what are the sequential steps to solving a network compression problem. What we have in front of us here is a table that shows activities, their predecessors, the durations, normal and crash, and the cost, also normal and crash. So it's required to calculate the normal, least cost, and crash durations for the following project. Calculate the cost associated with each duration. Indirect costs are $120 per day. So basically, for each day that you save from the duration, you're going to save $120. So the first step is looking at these activities. First of all, we're going to try to draw this as a network or as a Gantt chart to determine. First, we're going to draw it as a network to determine the critical path. We're going to look at where are the critical activities, which activities are compressible, and so on and so forth. The total direct cost for this project can be obtained by adding the normal cost for all activities, which is equal to $49.50. So as you can see here, when you add these normal costs, that's the sum of the direct cost of the project before compression. The total indirect cost can be obtained by solving the network and multiplying the total duration by the indirect cost per day. So the total cost of the project is total direct plus total indirect. The total direct was measured here by adding the normal cost before compression. The total indirect is going to be equal to the duration of the project that we calculate from the network times $120 per day, which is the indirect cost per day. When we add these two numbers, the $49.50 and the duration times 120, that would give us the total cost of the project before compression. What we're going to be doing gradually after each cycle of compression, we're going to compare this cost to the initial total cost before compression, and we're going to determine whether we are on the right side of the curve, which means as we compress the project, the total cost is going down, or on the left side of the curve, which means as we keep compressing the project, the total cost goes up. So here's the network based on the information that was given in the table. We drew the network, we have the durations. So what we're going to do next is basically calculate this network. And here are the dates based on the network calculation, which shows that the project is going to be expected to finish on day 25 and has one critical path, which is A, C, E, H. That's our critical path. 4 critical activities. The other activities we notice here, for example, on activity B, we have only 1 day of total float, so very close to being critical. Activity F, also 1 day. G, 1 day. And activity D, 2 days of total float. So this is a very tight network, which means after compression by 1 day, depending on the activity that we're going to compress, we might create some new critical paths, so we should expect more critical paths to appear as we compress this network. The total indirect cost in this case is going to be 25 days times $120, which is $3,000. So the total cost before compression is going to be $79.50. Now we're going to start looking based on the table at which activities are compressible, effective. In this case, by the way, as you notice, all the activities are finished to start, which means all of them are effective. Therefore, we're going to be looking at which activities are critical, A, C, E, H, which are compressible, we're going to look at the table, which are effective, all of them are effective, and then we're going to look at the critical, compressible, effective, least cost activity, which is going to cost the least to compress. This is going to be our prime candidate for compression. So here's our critical path. Looking at the other paths, ABAH 24, which means only 1 day of total float. ACFH 23, 2 days of total float. 1 day, 2 days, etc. Now looking at the cost slopes for the different activities from the initial table, we look at crash cost minus normal cost divided by normal duration minus crash duration, which is delta C divided by delta T. So in this case, it's 100 divided by 1. It is 150 divided by 2. it is 120 divided by 3, it is 200 divided by 4, 100 divided by 2, 0, activity F is incompressible, and then 150 and 120. Looking at the critical activities highlighted in red, we notice that the cheapest critical activity, critical, compressible, effective, is going to be activity C. By how many days can activity C be compressed? It can be compressed by 3 days. But we know that we cannot compress 3 in one step by 3 days because, again, other paths have only 1 day of total float or maybe maximum of 2. So if we compress C by 3 days, we definitely are going to create a new critical path without noticing it. So we have to keep an eye on the creation of new critical paths. So cycle 1 is going to be to compress activity C by 1 day. As the total float on B is only 1 day, once C is compressed, B becomes critical. The cost of compression in this case, based on the table, is going to be $40. So if I tell you right now that to compress the project by 1 day, by compressing activity C, you're going to incur an extra cost of $40 for the compression, which is the cost slope of C, and you're going to save $120. So the net is going to be savings of $80. That's definitely a good situation. So right now we are still moving on the right side of the curve. As we compress, the total cost goes down. Now to proceed with the second cycle, we have to check the cost slopes of activities to be compressed. Remember that in order to achieve an effective compression on more than one critical path, if you have more than one critical path, you have either to compare both paths by exactly the same amount. And that can be achieved either by compressing one activity on each path or finding a common activity on both paths that's cheaper to compress than the sum of the two activities on the different paths. So in this case, after the compression cycle number 1, we have savings of $80. And that shows now the numbers based on the compression cycle of activity 1. Notice here that the duration of C has been reduced to 7 days, which resulted in the new dates in green. And now on the backward pass, we notice that activity B has become critical. So now we have two critical paths, A, B, E, H, and A, C, E, H. A, C, E, H. Activity D still has 1 day, activity F has 1 day, and activity G still has 1 day. Now the options to compress this network. We can look at activity B and C together. We can look at activity E. We can look at activity H. Or we can look at activity A, whichever is going to be cheaper to compress. So now let's look at the numbers again. B by itself, $75. C, $40. So if you want to compress B and C together, then it's going to cost $115. E costs $50, which is cheaper. H costs $120, which is more expensive. A costs $100, which is cheaper than B and C combined. So probably the cheapest one to compress right now would be activity E, which can be compressed by up to 2 days. But again, going back here, we notice that the total float in this case is only 1 day on the other paths, so we cannot compress E in one step by 2 days. Therefore, the next step is to compress E by 1 day. This results in converting all the activities on the network into critical activities. A very interesting situation. But before we forget, that resulted in an extra cost of $50 and resulted in savings of $120. Therefore, the net is going to be savings of $70. So now we have reduced the duration of activity E from 6 to 5. And you notice here the purple numbers now, all the activities have 0 total float, which means right now we have how many critical paths? We have 4 separate critical paths. A, B, E, H, A, C, E, H, A, C, F, G, and A, D, G. 4 separate critical paths. So again, we're going to now need to compress all paths by the same amount. So if I want to compress, for example, the top 2 paths, E is still effective because it still has some compressibility, but I have to compress something together with E on the lower paths. So I'm going to need to compress, for example, G. G is a joint activity between the 2 bottom paths, by the way. So by compressing G by itself here, you're going to compress ACFG and ADG. So basically we can compress E and G if they are less expensive than other options like activity A, for example. Activity A is a joint activity, so by compressing A, you're going to compress the whole network. So now we have a whole network as a critical network. Looking at the numbers again. Activity D is $50. Activity G, quite expensive, $150. Activity B, 75, C, 40, but we have an activity F. For the first time now we have a critical activity that is incompressible, so we cannot compress activity F. Therefore, now we have 4 critical paths. It can be achieved by compressing at least one activity on each path or compressing common activities on all paths. The only one that's common is activity A. So A by itself is $100. B, C, and D, 3 critical paths, $165. E and G, $200. H and G, $270. Therefore, the cheapest to compress is activity A. Activity A can be compressed only by 1 day. So we're going to use that day to compress. And notice that the extra cost of compression is going to be $100, but yet we are still saving $120. So the net balance at the end is still going to be savings, which is still positive. We are still moving on the right side of the curve, but getting very close to that lowest cost point, beyond which any compression is going to result in an increase in the total cost of the project. Now we drop the duration of activity A to 4, and now we have compressed the network. All the activities are still critical. This number should be 11 and 4, by the way. There's a certain typo here. That should be 11 and 4, not 12 and 5. So now we have made the correction. It's a correct, the numbers are correct right now. As we can see, all the activities are critical. So that's the original critical path. That's the one created after the first cycle. That's the one created after, these are the ones created after the second cycle. So now we compressed A. We have compressed the project so far by 3 days in 3 consecutive cycles. So here's cycle 1, cycle 2, cycle 3, the cost for each one of them, and so on. Where to stop? The answer to this question depends on the objective we need to achieve. As you remember, we mentioned in class that the compression problem, the compression question, can be asked in one of 3 different ways. One of them is compress the network to the maximum until it cannot be compressed any further. Another one is compress the network until we reach the lowest cost point. By looking at this table, again, at the cost slopes, if you want to compress any further, going back here, if you try to compress any further, as you can see, it's going to cost you more than $120. So we're going to move to the left side of the curve. So if the question is compress until it's not economically feasible to compress any further, this is where we should stop. If the question is compress the network by, for example, 3 days, this is where we should stop. If the question is compress the network to the maximum, regardless of the cost, if the network still has any compressibility, we should keep going until we are done. All the activities cannot be compressed any further. This network still has some compressibility, so we can still keep going. So again, this basically says what I just said. If we need to compress the network to the maximum, we have to keep compressing until we exhaust all the compressibility on at least one path. Once one critical path becomes incompressible, then the whole network becomes incompressible, because if you try to shorten the other paths, that critical path is going to stay longer, and that defeats the purpose of compression. So once one critical path at least becomes exhausted with its compression, then the problem is over. We cannot compress any further. If we need to compress the network until it's not economically wise to compress it any further, we stop as soon as the cost of compression cannot be offset by the reduction to the indirect cost. So the increase in the cost slopes of the activities being compressed cannot be offset by the reduction or the savings from the indirect cost. If we need to compress the network by a certain number of days, then we need to stop as soon as we reach that time duration equivalent to that number of days. For example, if my project is 4 days behind schedule, why should I compress more than 4 days? It's not going to help me, because I'm probably going to pay more to compress beyond 4 days, so I should stop at the 4 days and avoid paying the liquidated damages. And this is basically the idea that we were talking about, that total cost curve. This is going to be the right side, and this is going to be the left side. Right now we have already reached this point, which is the lowest total cost, which is the optimum duration, so that's after 3 days of compression. Compressing any further is going to result in an increase to the cost. If you want to try, you can try on your own to keep compressing this network to the maximum, but this is basically where we're going to stop, assuming that the question was to compress the network until it was not economically feasible to compress any further, which is at this point, and we are already there. So basically this is our solved example on network compression. Remember, again, a few things to remember when solving this problem. First of all, you have to draw the network correctly. You have to calculate the normal durations in the network to get the expected completion date. You calculate the total indirect cost by multiplying that date times the cost per day, the indirect cost per day. The total normal cost or the total direct cost can be calculated by adding all the normal costs. Adding the total indirect plus the total direct gives you the total cost of the project before compression. Always keep an eye on the near critical activities, which have very low amount of total float, because once you start compressing, you may cause these activities to become critical, and therefore creating additional critical paths, which is going to require parallel compression of these paths. Remember that if you have two critical paths and you compress one activity on each path, that results in only 1 day of shortening of the project, because these paths are in parallel. So it's not you compressed 1 day on activity B, for example, and 1 day on activity C, but this resulted, since they are on parallel paths, resulted in only 1 day of compression to the whole project. If you have 3 critical paths and you compress one activity on each, again, you compress 3 activities by 1 day each, but since they were running in parallel, that resulted in only 1 day of compression for the whole project. If you have a total float, the minimum total float on the network, let's say, is 5 days. Then in this case, if an activity can be compressed by 3 days, you can do that in one step to save yourself some time, because you know that by compressing this activity by 3 days, you are still going to have a minimum of 2 days of total float on the other paths, so you're not going to create any new critical paths. One last thing, and this is very tricky part here. You may have some activities that are ineffective on one path, yet they might be effective on another path. So for example, if I have a network, the initial critical path had a start-to-start relationship and a finish-to-finish relationship. If you remember, per the definition of the effective activities, the start-to-start would make the first activity ineffective, the finish-to-finish would make the second activity ineffective. So on that particular path, these activities are ineffective. But let's say we have created a new critical path, and that contained these same activities, let's say the first and the last activities, in a finish-to-start relationship with the other activities. Then the first and the last activities are still ineffective on the first path because the start-to-start and finish-to-finish relationship, but They are effective activities on the second path because they are finish to start activities. So they can be used on one path and not on another. Remember that, because again, that might be a question on a test. Good luck, and I'll see you on the test.